And for that reason, I'll use bracket notation like TI to denote the ith entry of T. Okay. And suppose the verifier is handed as input a commitment, let me call it com A, to a vector A. Let's say A has length M. Okay. In a lookup argument, the prover claims that every entry of A resides somewhere in the lookup table. So every entry of A is somewhere in the table. Okay, so formally that means for every entry AI in A, there is some K in, K is an index into the table such that AI equals TK. So that's what it means for AI to reside somewhere in the table. Okay. And so formally, a lookup argument is a snark for the prover's claim. And more precisely, to be maximally precise about the claim, a lookup argument is a snark for the claim that the prover knows an opening A of com A. So an opening A in field of the M of the commitment such that the above holds, every entry of A resides somewhere in the table. Okay. So that might be a little bit abstract, I guess it's reasonably straightforward. I mean, the prover's just committed to some vector A and proves to the, lookup argument lets the prover prove to the verifier that every entry of A is somewhere in the table. I guess that's easy enough to understand. But let's see an example real fast to make it more concrete. So let's talk about range checks. Suppose a prover has committed to a vector A, and the prover claims that every entry of A is in the range, let's say 0 up to 2 to the 64 minus 1. Okay, and this sort of situation arises not that infrequently, whereby like if some value arising in a computation is like larger than some threshold, some kind of overflow error might occur, and so the verifier has to become convinced that no value is above this threshold. If one of them were, then the verifier could actually commit to a value bigger than the threshold, and that might kind of screw up the verifier's checks. So this is called a range proof. And this can also arise where maybe somebody, a roll-up commits to a bunch of transaction amounts, and if any of them were like negative, they would be invalid transactions. Like maybe I'm not allowed to initiate a transaction that transfers a negative amount of money from me to Alice, because that would be equivalent to me taking money out of Alice's account and putting it into mine. And so, a range proof would say, hey, I'm going to declare like valid transaction amounts to be, some number of, sats, if your range is going to be this big, between 0 and 2 to the 64 minus 1, and anything outside of the range, I'm going to think of as like a negative number or something and not allow it. Okay, so the sort of before lookup arguments came about, the traditional way to prove this would be the following. So you would have the prover provides as untrusted advice the bit decomposition of each entry of A. Let's just fix an I, an entry AI of A. Just so I don't have to sort of carry I along in all my notation. So let's focus on one entry of AI that the prover wants to prove is in this range. So the prover would provide as untrusted advice, let's say 64 values, 64 field elements, B1 to B64, which if the prover is honest, so these are purported to be the binary representation of AI. And what that means is if the prover is honest, each of these is a bit, each of these is in 0, 1. So each BI, B1 up to B64 is in 0, 1. And AI is the sum over all of these bits, j equals 1 to 64, of 2 to the j minus 1 times bj. Okay, and like if the verifier confirms that indeed each of these bits are in 0, 1, and this weighted sum of the bits is AI, then that guarantees that AI is between 0 and 2 to the 64, just because this kind of weighted, any weighted, this sum, applied to any bit vector, any B1 to B64 in 0, 1 is a number in between 0 and 2 to the 64. So that's the kind of traditional way to do a range proof. And the problem is this is pretty expensive. What we have here is to do a single range check, the prover committed to 64 field elements. These B1 to B64, and also the verifier had to include 65 constraints. Okay, so for each, what are these 65 constraints? To insist that each of these BJ's is in 0, 1, you have to include the constraint that BJ squared minus BJ equals 0. So this is like the way of expressing the property that each BJ is in 0, 1 as sort of a degree 2 constraint. And then you have your 65th constraint here that AI is the appropriate weighted sum of the BJ's. And that's just like a very expensive way to do a single range check that on your laptop would just be like one primitive instruction. Okay. So lookup arguments offer a potentially more efficient way to do this. So you can just rephrase this range check directly as the problem that lookup arguments solve. So you can use a lookup argument, and all I have to do is tell you what is the table. And the table is, so the predetermined table is just T, whose ith entry is just the number I, or the field element I, right? So that is, the ith entry of T is just I, as I ranges from 0 up to 2 to the 64 minus 1. And here, this is I interpreted as a field element. Okay, so then, one range check is just one lookup into the table, meaning, to confirm that a given entry of A, maybe I want to use J here, just since I was using I to denote indices into A. So AI being in the range is equivalent to, is the same thing as AI being in the table. So it's the same thing as there exists a K such that AI equals TK for this particular table. Okay, so if I give you a lookup argument where kind of the commitment cost for the prover is fewer than like 64 field elements per lookup into a table of this size, I've sort of done better, given you a better range check than the sort of naive old approach of just doing bit decomposition, of having the prover commit to the binary decomposition of each entry of A, um, as untrusted advice, and then confirming that each untrusted advice input is indeed in 0, 1, and that it's indeed the binary decomposition of the appropriate entry of A. Now, of course, I shouldn't say of course, I'll just tell you, in existing lookup arguments, an honest party has to commit to the table in pre-processing, which means actually using a table of size 2 to the 64 is not tenable. And I'll explain later certain ways you can avoid that, both using existing techniques, and this is a perspective I'm sort of developing in some new work that I'm hoping to share soon. Okay, so let me just pause here, since I've been talking for 15 minutes without pausing, see if there are any questions. But yeah, hopefully we at least understand at this point what is a lookup argument. I haven't told you at all about how they actually work. No questions? Okay, someone want to confirm you can hear me and see my screen?
Yeah, we can see.
Okay, great, cool, thanks. Okay, so yeah, I want to make one more comment before we actually start talking about how lookup arguments work, which is lookup arguments are useful. In particular, they improve over the bit decomposition approach in settings, I guess, involving many lookups. Right. So I'll tell you in a moment the costs of some important lookup schemes, but basically there will be some kind of how do I want to put this? Okay, there will always be some kind of cost for the prover that depends on the table size. Yeah, depends on the table size. I'm calling that N, capital N. But depends, like either has no dependence at all or has just a very mild dependence on the number of lookups M. Okay. So the cost will be something like, I'm going to cover something today where the cost will be, I don't know, something like M plus order N log M. We'll see others where the cost is like order, like max M comma N, and so on. And the point is, like, if M is small relative to N, then this cost that depends on N is dominant, and so that's actually would be worse than bit decomposition potentially. Okay, but if you have a lot of lookups, if M, say M is like much bigger than N log M, or in this case M is much bigger than just N, then this can be better than bit decomposition, because basically you wind up amortizing the costs that depend on the size of the table across all of the lookups. So kind of whereas bit decomposition in my example above cost like 64 committed field elements per lookup. Here, the cost per lookup might be much smaller than 64 committed field elements. And as long as, this sort of cost that doesn't grow quickly or at all with M, as long as that's low order compared to the cost that does grow with M, then you can kind of ignore it. And so, yeah, lookup arguments are useful in these sort of amortized contexts where you're doing multiple lookups. But if you really just wanted to, do like one range check and that's it, bit decomposition would be the way to go, because it wouldn't make sense to pay this cost that depends on the size of the table. Okay, any questions about that?
Isn't there a lookup argument that doesn't depend on the table? I think.
Um, okay, so the question was, is there a lookup argument where the prover's costs don't depend on the table size? So there isn't like such a term like this? Was that the question?
Um, so I think CQ doesn't depend on the table.
Okay.
Uh,
Yeah, good. So good. So I'm about to just do like a quick summary of like known lookup arguments and tell you what their costs are. But in a sentence, so CQ is the latest in a line of work starting with caulk. So there was caulk plus. I think I forget if there were two pluses or one plus in caulk. Caulk plus. Yeah, I think lookup was somewhere in this line of work, and CQ, and I might be missing. Oh, there was Baloo. Okay, so what CQ does, what all of these do is they seek to they push the costs that do grow with the table size to a pre-processing phase. So I'll just tell you right now what the costs of CQ are. So in pre-processing, this was what has to happen in CQ. So an honest party commits to the table, so commits to the vector T using KZG commitments. So these are all actually tailored to KZG commitments. So they're interpreting T as like a univariate polynomial, like, I don't know, the coefficients of it or something. Okay, so that is, that needs a structured reference string of size equal to the table size. And yeah, it has to be committed by an honest party because an untrusted prover can't be trusted to commit to the correct table. Okay, and that so I think that's that's fine if n isn't too big, but like if your table has size 2 to the 33 or something, even 2 to the 30, we don't even have SRSs that big, and they'd be like many gigabytes in size or something. On top of that, the prover, this can now be the untrusted prover, in CQ does something like n log n group exponentiations, which is significantly more expensive even than the time required to commit to T using KZG commitments. The nice thing is this is a one-time cost for the table, per table. So if you want to use a certain table across, many different snarks, or the same snark applied many different times or something, you do this expensive setup once, and that's it. And then so once the setup is done, the prover cost in CQ is I think it's like order M. M is the number of lookups. Group exponentiations. No, you know what? No, okay. I think it's slightly better. It's order M. It's something like 7 or 8 order M sized multi-exponentiations, also known as multi-scalar multiplications, and something like order M log n field work or something like that. Okay, so short version is, people are really excited about CQ because like it has pretty good prover costs, even when the table's big. If you ignore the pretty expensive pre-processing that does have costs that are actually even super linear in the table size. Is that helpful?
Yes, thank you.
Yeah, and yeah, and that it's important to it doesn't totally get rid of these costs that depend on the table, but it pushes them all to pre-processing, so they only have to be paid once, and that sort of mitigates this nuisance that with before caulk and stuff, you needed like to have more lookups than you had entries in your table for it to like kind of ever make sense to use a lookup argument, I guess. Otherwise, you should probably just be using bit decomposition, unless your number of lookups got pretty close to the size of your table. Didn't have to strictly be more, just because the bit decomposition is committing to like some kind of roughly logarithmically many field elements per lookups. So if your number of lookups was like table size over some log factor, that might actually be enough for it to make sense to use a lookup argument. But anyway, you couldn't be like way less than table size many lookups for it to make sense to use a lookup argument until Calc set off this line of work that pushed the gross crypto costs that depend on the size of the table to a pre-processing phase. Okay, so so now you've actually seen the costs of like a state-of-the-art lookup argument like CQ. So let me tell you the cost of some earlier lookup arguments. So the first lookup argument is in a paper called ARIA due to Jonathan Boodle and Jens Groth and others, and that's actually what I'm going to cover today in detail. And here the cost is roughly, I think it's actually just the commitment cost for the prover is roughly like n log m, committing to order n log m field elements. And the exact cost of that is going to depend on what polynomial commitment scheme you use to commit to those field elements. Then Plookup was a follow-up work whose cost is something like the prover commits to 5 times the max of m and n many field elements. Okay. And so, by the way, this is everything I'm stating is in addition to this an honest party committing to the table in pre-processing. You interpret the table as some kind of polynomial, and you take its low degree extension polynomial or something, and an honest party has to commit to that in pre-processing. And all of these lookup arguments that are published today, I have some new work coming out that's going to get rid of that for tables that have some structure to them. Okay, and so what's happening here is like if m is like much bigger than n log m, then ARIA's costs are actually better than Plookup's. Because if let me make sure I'm saying this right. Right. If m is much bigger than n, or n log m, then m becomes the dominant term down here, and you have this leading factor of 5, which is not great. So that's the setting where ARIA shines, is when you have like really like a ton of lookups into a table. Like, so the number of lookups is much bigger than the size of the table. But if the number of lookups is a little bit smaller than the size of the table, or not that much bigger than the size of the table, Plookup will be better, because basically you can think of m and n in this setting as roughly the same, and you're cutting off this log m factor that exists in ARIA. Okay, questions about these two? Good. Okay, and then there's been some more recent lookup arguments. One is in a Hyperplonk, and one is in a paper by Ulrich from Polygon. And I forget Ulrich's last name, so I'll just say Ulrich's paper. And these are both lookup arguments using the sumcheck protocol. Ulrich's paper in particular combines sumcheck with something called logarithmic derivatives. I'm not going to discuss the details of this. And the short version is these both improve on Plookup in various ways. While targeting the same sort of parameter regime, roughly that m and n being about the same in magnitude. ARIA, I think, is still like the natural thing you would want to do based on current currently published lookup arguments if M was way, way, way bigger than the table size. But there are already some improvements to lookup as people have sort of been catching on to the power of the sumcheck protocol. Okay, I'm sure I'm missing like some lookup arguments, but this is pretty comprehensive summary of the state of the art, I think. Yeah, apologies if I'm missing a handful, but yeah, this is a decent overview. Okay, so with all that out of the way, today I just want to discuss ARIA. I think ARIA is nice and conceptually simple. And yeah, I think it'll convey like the main ideas of how these lookup arguments work. It'll also cover details of a key technique that I didn't discuss in full detail last week that comes up even in like a general purpose backend like Plonk, this sort of permutation checking thing. So I'll say more about that later. And then next week, I think what I plan to do is to sketch lookup without covering all the details. Then start talking about sparse polynomial commitment schemes. And I'm hoping the week after that, well, okay, let me just say sparse polynomial commitment schemes plus this new lookup argument that I'm hoping to release publicly soon. Okay, so that's today we'll just cover ARIA, and then next week we'll see lookup, and then move to some of the latest and greatest stuff. And there are some ideas in this new lookup argument, related to like the calc, line of work that has led to CQ. So you'll, hopefully you'll get some flavor of like how this calc line of work goes by seeing how this new lookup argument that's not published yet works. Okay, so let's start with ARIA. All right, so let me just gather my thoughts for a second how I want to present this. Let's see. Okay. Yeah. So you remember in a lookup argument, let me quickly remind you what the setup is. So the prover has already committed to some vector A in field to the M. Claims that every entry of A, so every entry AI of A is somewhere in the table. And the table we're thinking of as a vector of length N. And so in ARIA, the prover first commits, to a witness for this claim. Okay. And it's sort of a funny witness. That witness is the multiplicities of every table element. And what that means is it's a list of n numbers, one per table element. Let me call them E1 to En, where if the prover's honest, EI, let me say EJ, I guess, since I'm trying to use I to denote entries of A. EJ is the number of times the jth entry of T appears in A. Okay. That's what multiplicities mean. Okay. And let's see. In ARIA, for reasons that will become clear shortly, the EJs are not specified as individual numbers or field elements, but they're given instead by their binary representations. So they're in 0, 1 to the log M, where M is the length of A. And so that way, these are just the binary representations of these multiplicities. Any log M bit number is the binary representation of some number in 0 up to M minus 1. yeah, I guess that's annoying. Like you could have a case where if A has length m, every single entry of A is equal to the same thing, and then the frequency that would be m. So that, yeah, okay. Let's just say that's some annoying off by one thing. I guess it needs to be log of m plus one, and that way the numbers are between 0 and m. But yeah, this is just some gross technicality. Let's just ignore it. That's just trying to cover the case where every entry of A is the same, and then something has frequency m. Okay, so yeah, so conceptually, I guess the prover has sort of already committed to A at the start of the lookup argument, and then the lookup argument prover commits to these multiplicities E1 to En, but of course they're specified as bit vectors in 0, 1 to the log m. Okay, and now basically what we're going to do is we're going to design a circuit. This is a little sketchy and not entirely true, but it's pretty close to true. We're going to design a circuit that just checks, that, for each EI or EJ is actually the multiplicity of TJ. Okay. And so how is the circuit going to do that check? Okay, so here's the key claim. Okay, so this check, each EJ is indeed the multiplicity of TJ and A, if and only if the following holds. So this property is equivalent to the claim, or the condition that the following two vectors are permutations of each other. Okay. And by permutations, I mean they have the same entries up to reordering. Okay, so one of the two vectors is just A, and the other vector is the vector where like the first entry of T is repeated E1 times. I know I'm using notation here, right? Like E1 is actually a bit vector between 0 and log m, and I'm interpreting it as an integer here instead of as a bit vector. T2 appears E2 times, is repeated E2 times, and so forth. Tn is repeated En times. Okay, and what's happening in this claim, like shouldn't even really require like a written proof. It's just like if the EJs are indeed like the multiplicity of TJ and A, then this vector here, all it's simply doing is it's taking the entries of A, and it's just grouping them or sorting them by entries of T. So like all of the entries of A equal to T1, in this vector here, like come first, all E1 of them. All of the entries of A equal to T2 in this vector come next, and so on and so forth. So if the multiplicities, the EJs are honestly specified, then this vector down here is just a reordering or sorting of A itself. Yeah, and so in particular, if A contains some entry that's not in T, there is no way that this vector down here is a permutation of A, just because this vector down here is guaranteed to not have any entry that's not in T, just by definition. It only repeats entries from T itself. There's no way to get into this vector down here some field element that's not in the table. In particular, if the prover's claim in the lookup argument is false because there's some entry of A that's not in the table, there's no way for the prover to specify a multiplicity or a sequence of multiplicities to make these two vectors permutations of each other. Okay, questions about this? Okay. Yeah. So
Could you like
yeah.
put this in terms of like the range check?
example?
Yeah, great. Yeah. So I guess let's just say, okay, let me just do an example. So let's say A is, maybe it's nice to keep things in power too. So let's say there are 8 entries of A. I'll just make them up now: 7, 18, 4, 3, 2, 1, 2, 3, 4, 5, 6, 8, 4. Okay. Let's say that's A. I think that's 8 entries. And then in the range check, I had said the range would be 2 to 64 minus 1. That's actually too big to directly have as a table now. So let's just make the range 2 to the 16 minus 1, just to make it something you could actually apply like existing lookup argument to. And in that case, so this would be the table. And the multiplicities would be the following. So the first entry of T, I've been indexing T by starting at 1. That's annoying in this case. Let's index it from 0. So like E0 would be 0 because the number 0 doesn't appear in the table at all. And in A at all. And E1, so the second entry of T, which is equal to 1, its frequency is also 0, because it doesn't appear in the table. But E2 would be 1, it looks like, because 2 appears once in, I keep saying the table, I mean A. Yeah, so the number 2, which is the third entry of the table, appears once in A, and hence its frequency is 1. And again, this is a abusive notation. I'm writing down, the multiplicity as integers, but really they wind up being specified by the prover as in binary. So if A has length 8, then each of these things would actually be 3-bit numbers to represent, numbers between 0 and 7 or 0 and 8. Or again, there's this annoying kind of off by 1 thing. So yeah, I guess really, whatever. Let me not get hung up on it. So really E0 would be 0, 0, 0 to represent frequency 0. E2 would be 0, 0, 1 to represent multiplicity 1. E3 would, I think 3 appears once in A. And E4, I think 4 appears twice in A, if I did that right. So that would be multiplicity 2, and binary, that's 0, 1, 0. And hopefully that's enough examples, because I'm obviously not going to write down 2 to the 16 multiplicities. Is that helpful? Is that what the sort of thing you were looking for?
Yeah, that's what I thought. That's just what I expected. Yeah, thanks.
Yeah, okay. Thanks for asking for that. Yeah. Other questions? Cool. Okay. Yeah, so essentially what the circuit is going to have to do is just check that A and this funny vector here, obtained by repeating table entries a certain number of times as specified by the multiplicities, that they're permutations of each other. Okay, so let me just take a step back, or kind of a step up in abstraction, and let's forget about this particular funky vector. Let's just talk about permutation checking. Okay, and this we did discuss last week, and I said I'd cover the details this week, and so here they are. So let's say we're just given, like, the prover has committed, let's say, to 2 vectors, A and B. Let's say they're both in field to the M, and claims they are permutations of each other. So they have the same entries up to reordering. How can the verifier be convinced of this, of each other? Okay, so the way to do this is the following. And we discussed last week what I called interactive reductions to circuit sat. And that is basically my way of viewing how you have to deal with circuits that want to execute a randomized algorithm, a randomized checking procedure. And so that's what's going to happen here. Okay, so A and B are already committed. It's critical that they already be committed before the following happens. The verifier picks a random value R. Okay. And in practice, R is, so this is a random field element. In practice, this will be chosen via fiat Shamir by hashing the commitments to A and B. And the circuit will essentially run a randomized algorithm. So the circuit implements this randomized algorithm with R. The randomized algorithm only needs one random field element. That's the randomness to the algorithm. So R is the randomness. To check that A and B are permutations of each other. Okay. Okay, so that's it. So you apply like a snark for circuit sat to the circuit. Of course, I'm going to tell you in a moment what the randomized algorithm is. And in that way, the prover proves that, like A and B passed the check of this randomized algorithm that checks whether, its two inputs are permutations of each other. Okay. Questions about that? Okay. So what we need is like a fast randomized algorithm to check that these two vectors are permutations of each other. So let me just call that permutation checking. Okay. Moreover, it can't just be fast like when you run it on a laptop. It needs to be fast when implemented inside a circuit, right? So so that naturally, like turns into or can be implemented within an arithmetic circuit. All right, so like if the algorithm does a bunch of like bitwise ends or weird operations that your laptop can do really easily, but circuits with just finite field additions and multiplications can't do easily, that's going to be a problem because it'll run fast on your laptop, but it won't turn into a nice circuit. So fortunately, there's a very simple algorithm, as we'll see, that does turn directly into a circuit. Okay, so here it is. The algorithm simply checks that the following two products are equal, so that the following equality holds. Okay, so the product over all entries of AI minus R equals the product over all entries of B of the same thing. Okay, and so I call this permutation invariant fingerprinting. That's my terminology. Okay, it's closely analogous to what I called Reed-Solomon fingerprinting that we discussed in like the second meeting of this group. In Reed-Solomon fingerprinting, the entries the one wanted to check whether two vectors A and B were equal. Okay, and to do so, one interpreted the entries of A and B as like the coefficients of a degree M polynomial or M minus one or whatever, and evaluated the associated polynomials at a random point. And obviously, if the two vectors were equal, you'd be evaluating the same polynomial at a random point and you get out the same thing. But if the two vectors differed in even a single entry, you'd be evaluating two different degree M polynomials at the same point. And because any two distinct low degree polynomials can agree at only a few points, the probability over the choice of random point that they would agree is very small. Okay, here what we're doing is rather than interpreting the entries of A and B as coefficients of a polynomial, or in the case of like low degree extension codes, evaluations over some interpolating set of a polynomial, we are instead interpreting the entries of A and B, so like the entries of A, as the roots of the polynomial. Degree M or M minus one polynomial, and similarly for B. And the key point is that it doesn't matter like what order the roots of a polynomial come in, it's still the same polynomial. So, but roots are just, you probably all know this, it's okay if you don't, just in case anyone doesn't. It's just the inputs at which the polynomial evaluates to zero. Okay, so the polynomial here that I'm referring to is the polynomial, let me just call it, I don't know, PA of t is the product I equals 1 to m of ai minus t. And so, by design, this is the polynomial whose roots are given by the entries of a. If you feed in t equals ai, you get ai minus ai, which is 0, and the whole product evaluates to 0. And the multiplicity of a given root is just the number of times it appears in the table. In A. Let me not use t since I'm using that to denote our lookup tables. Yeah, and like another way of just saying this is, of course, that finite field multiplication is commutative. So you can take, two vectors that have the same entries but in different orders, and if you, subtract r from each entry and product out the results, you get the same thing, regardless of the orders of the vectors. Okay, yeah. So in summary, what this algorithm is doing is interpreting a and b as two polynomials whose roots are given by the entries of a and b, and the algorithm is just picking a random point r and evaluating these two polynomials at that point. So it's checking whether PA of r equals PB of r. Okay, and if A and B are the same up to permutation, PA and PB are the same polynomial. So of course PA of r equals PB of r. But if A and B are not permutations of each other, PA and PB are different polynomials, and they both have degree m. So the probability in that case that PA of r equals PB of r, the probability over the random choice of r is only at most like m over field size. So that is how you do permutation checking via a randomized algorithm. Okay, and then the fact that this product here and this product here just involve with x fixed to r. For each entry of A and each entry of B, it's just you subtract r and you product out the results. So that's something that's very easy to do inside a circuit. So let me actually just draw that circuit out, which is maybe belaboring something that's pretty much obvious, but just to make sure we're kind of all on the same page. Let's call this, I don't know, A0, A1, A2. Let's just say that, that's all the entries of A, B0, B1, B2. Those are the entries of B. So, for each entry of A and B, you'd have a subtraction gate. And so you subtract R from each of these things. So yeah, you get the idea. And then it's a little annoying that it's nice to have things be power 2 so I can have a complete binary tree. Unfortunately, I didn't do that here. So I won't draw a complete binary tree, but yeah, so via some kind of tree of product gates, you can product together all of these terms. And so this thing here that I just drew, this is the product over all entries of A of AI minus R. And then also, same thing over here, you can have a little, tree of product gates, each of fan and 2, to get the product BI minus R over all entries of B. And you can either declare these to be the two output gates of the circuit, and the verifier on its own will check that they're equal, or you could subtract them from each other to have a single output gate which the verifier insists is going to be 0. So either way. That is how you do permutation checking, like in a circuit. All right. Okay, does that make sense? All right, and so you can just apply like any snark for circuit satisfiability. I mean, here the prover has kind of already committed to the full input to the circuit, A and B, and then R is determined by Fiat-Shamir hashing. So really, circuit evaluation is actually enough at that point. And so this circuit kind of just confirms that A and B are permutations of each other, with overwhelming probability over the random choice of R, which you think of as either being chosen by the verifier after the prover has committed to A and B, or as being chosen via Fiat-Shamir hashing by hashing the commitments to A and B. Now, I want to point something out here. This, I drew this small example, but in general, it would be, these products would be really big, right? Like, this in a lookup argument, M is the number of lookups, and we're thinking of there as being like a large number of lookups into the lookup table. So this is a product of many different terms. Okay, and snarks for computing products like that, they're called grand product arguments. And they come up all over the place, in part because this permutation checking thing comes up all over the place. So it came up last week in how we were achieving checks for what I called memory consistency. So I don't want to, belabor the point of reviewing what we discussed last week, but in a couple sentences, if the prover, claimed that it ran some computer program for a certain number of steps, the way front ends roughly work to put out an equivalent instance of circuit sat is the circuit will take as untrusted advice an entire execution trace of the computer program, run for all those steps on the appropriate input. And one thing that the verifier has to check is what's called, or the circuit has to check, is what's called memory consistency of the trace, which just means that the value returned by every read operation done by the computer program is correct, meaning is equal to the value most recently written to that memory cell that was read. And the way that people check that today, so that property is called memory consistency, is they will have the circuit take a second execution trace as untrusted advice, where the second execution trace is reordered to be sort of sorted by memory cell. That is, which memory cell was actually read or written during that step of the computer program. And sort of once you have a sort of second execution trace provided that is a resorting of the first one by memory cell, it's very easy to check memory consistency because kind of everything that touched a given memory cell is sort of contiguously together in the execution trace. So the core of memory consistency checking turns out to just be confirming that two execution traces of a computer program are permutations of each other, or just reorderings of each other. And this is exactly how that gets done. So you see this come up in what's called memory consistency checking, or just memory checking. You also see this come up, like Planck itself just uses something like this. It's Planck is a general purpose backend for circuit sat, and it uses like a permutation check inside of it. So these grand product arguments come up all over the place. Okay. And there's something that's underappreciated about them. So I'm going to highlight it for you today, which is like the way the most popular snarks today, like Planck or Starks, would check a grand product, is they would have the prover commit to the value of every gate in the circuit I drew above. Okay, and so the way I described computing the grand product in the circuit was via a binary tree of multiplication gates. But actually, like Planck's grand product argument doesn't use a binary tree. It just uses like a length m sequence of multiplications, which is also fine. If you're going to commit to all these values anyway, it really doesn't matter if it's a binary tree or a long chain. But the point that's underappreciated is that the sum check protocol offers an alternative, and actually you could really even just use the GKR protocol directly. And this is what I was saying before, which is this circuit that just does the subtractions to get the terms that then need to be producted out in the grand product. If you do it with a binary tree of multiplication gates, that is a logarithmic depth circuit, and the inputs to that circuit have already been committed. So kind of what's left is actually just a circuit evaluation problem over committed inputs. And so you don't actually need any more cryptography. You don't have to have the prover commit to the value of every gate in the circuit. You can just apply the GKR protocol, and the prover can prove it correctly evaluated the circuit on these inputs with no commitments, with no commitments to the values of these gates inside the circuit, beyond No commitments beyond what was already committed, the inputs to the circuit. So A, B, and R. Okay, so this is just like a generic way to like actually speed up the prover in like all grand product arguments that are used today, is just like, don't use these techniques that have the prover commit to a value for every gate in the circuit. Just use the sum check protocol instead. Now, the proof size of like the GKR protocol is like annoyingly large. So that is sort of a downside of this approach. But you can kind of combine the two approaches to sort of get the best of both worlds, where you cut out like most of the proof size, reducing the proof size from like log squared down to log, while not really having the prover commit to most of the values of these multiplication gates in the circuit. So by sort of committing to just the values of the multiplication gates sort of near the output, you sort of save most of the proof size, but don't pay a significant amount in terms of commitment costs, because most of the gates in the binary tree are near the leaves and not near the root. Okay, so that was a bit of an aside, but that is, we have now discussed, snarks for permutation checking. So snarks for confirming two committed vectors are permutations of each other. Okay, so let's now go back to ARIA. And so we're almost just done today's session. So in ARIA, remember the prover at the start of the lookup argument before, had already committed to A. Okay, and then within the lookup argument, the prover commits to these multiplicities, E1 to En. Each of them is a vector in 0, 1 to the log m. Okay, and what we wanted to do is we wanted to check, so, conceptually, we want to sort of feed these two things into a circuit that we want to check that A and some other vector B, which is a little gross to define, but I'll remind you what B is in a second, are permutations of each other. So let me just say they're perms of each other. And let me just remind you what B is. B is the vector where the first entry of the table appears E1 times. The second entry of the table appears E2 times. The nth entry of the table appears En times. Okay. And remember, the way we do permutation, so the circuit is just going to apply the permutation checking procedure we just saw to these two vectors. Okay. It's a little annoying to explain how it applies it to B, just because B has this like weird definition in terms of the entries of T and the entry and these multiplicities EI. Okay, so that's all that remains, is to tell you like how do you apply the permutation checking procedure to this particular B, which is defined in this weird way. So that I'm going to do my best to do that, and then we're done for the day. So just as a reminder, let me remind you what's done to A by the permutation checking procedure. And we already saw this. So there's a subtraction, right? So that there's this random field element R, which is like chosen by the verifier after the prover's already committed to A in the multiplicities. You got a subtraction gate, for each entry of A to subtract R from it. And then you have this binary tree of multiplication gates to product all the results together. Okay, and that gives you the product from I equals 1 to M of AI minus R. Great. So the question is, how do you get the analogous thing for this vector B that I just described and erased, where T1 appears E1 times, T2 appears E2 times, and so forth? Okay, so that product for that particular vector B, that equals the following. So it's the product from I equals 1 to N of the ith entry of T, and maybe I want to call this J instead of I, just since it's ranging from 1 to N instead of 1 to M, minus R, okay, to the EJ, where again, I'm using notation now. This is, EJ as an integer, not as a bit string. Okay, and that's because, by definition, this entry, this vector B had TJ appear EJ times. And so this is, you get if TJ appears EJ times in B, then, in this big product here, you get TJ minus R EJ times, right? So the question is now just how do you compute this product? Okay, and basically, the answer is, the circuit, just as it did for A, will compute TJ minus R for each entry of T. I'll come back to that in a moment. But yeah, so you would have these subtraction gates that compute the appropriate terms of this size and product. And then the question is for each of those terms, how do you raise the jth term to power EJ? Okay. Yeah. So let me explain that. So that is just the standard. I guess you would call it square and multiply algorithm. This is just the standard way to, take some number. Let me just call it C, and some power. Let me call it E, and compute this. Yeah. Let me explain that algorithm. Yeah, I kind of didn't do a great job of this last night, but hopefully I'll do a slightly better job today. I guess it's going to be easiest with an example. So let's say, okay, so it's helpful to think of the exponent as expressed in binary, which is exactly what this circuit has done by expressing these multiplicities in binary. So let's say the exponent is 1101, which is the binary representation of the integer 13. So what we're doing is we want to compute C to the 13th power. Okay, so this is how the square and multiply algorithm works. So it maintains two quantities at all times. Let me call them, I don't know, P and Q. So P is going to be, it's going to start out as 1, I guess, and at all times it should be like the running answer, if you will. So the algorithm is going to go bit by bit over the exponents and kind of update the answer to, it's going to kind of compute C to the 13, kind of one bit of the exponent at a time. And so, after it's processed the first bit, it's kind of, incorporated it, in this example, it will have P will be set to C because that's C to the 1. After it processes the second bit, P will still be C because that's, C to the the number represented by 0 followed by 1, which is still 1, and so forth. And then there's going to be Q, which I guess will also start. No, I guess Q will start as C, and this will, after J steps, store C to the 2 to the J. Okay. So I think this will become clear just after an example. So yeah, let's run through this example. So before processing this first bit of the exponent, again, P stores 1 and Q stores C. Okay, but then when you go to process the first bit of the exponent, that bit is 1. And so the algorithm, sort of says, well, I'll just write it out. For each bit of the exponent, okay, if that bit, so I guess I'll do, this is going to be confusing, but I'll just call that EJ, even though it's it's different than the EJ up here because okay, maybe I'll call it E. Okay, let me just call this EJ to match this EJ, and let me call this EJ comma K. So if that bit EJK is 1, you update P to you multiply it by C. Okay, otherwise you just don't update P. Okay, and then you update C to be, not C, you update Q to be Q squared. That's the whole algorithm. So this is it. This is a square and multiply algorithm. So in this example, you start with like P being 1 and Q being C, and then because the first bit of the exponent is 1, P becomes C, and Q gets updated to C squared. And because the second bit of the exponent is 0, you don't update P, it stays C. Okay, so you move on to the, and I guess, and you update C squared, you square it to get Q to the C to the 4th. And then because the third bit is 1, you do update C. So you do update P. So you multiply these two things together. So P gets updated to C to the 5th with just like one multiplication. And then you square Q again. So Q gets updated to Q to the 8th. And you move on to process the final bit. And because that's 1, you multiply these two things together again. So P gets updated to C to the 13th, which was what we wanted. So in summary, the square and multiply algorithm just kind of goes bit by bit through the exponent and updates the running answer appropriately based on whether that's bits 0 or 1. And this algorithm turns directly into a circuit. So the only nuisance is this conditional statement, because conditionals are like a little obnoxious to represent in circuits. But because each bit, because the exponents are described as bits. Now, of course, the circuit, by the way, since these are untrusted, is going to have to do a Booleanity check. So it's going to have to include like a constraint or a gate that for each bit of each multiplicity, and insists that EJ, that bit squared minus that bit is 0 to ensure that it's in 0, 1. Only the value 0, 1 have that property. But yeah, so let's not dwell on that. So what happens to implement this if statement is as follows. So if let's say we have two gates that after k steps of this algorithm have computed the current value of P and the current value of Q, and what we do. So note the updated values of P and Q, or of P, is the following. If EJK is 1, we should multiply P by, I'm sorry, this should have been P times Q. Sorry about that. We should multiply P and Q together, and otherwise we should just multiply P by 1. So the new value of P should be, what is it? It's 1 minus EJK. So that's sort of picking out that EJK is 0. And in that case, we don't want to update P. We want it to stay P. But if EJK is 1, we want to update P by multiplying it by Q. Okay, so this is the desired new value of P. It's either equal to the old value of P if EJK was 0, or P times Q if EJK is 1. And so the circuit would just sort of for log m steps, it would so you'd have it would have a gate computing like P and Q at each of the log m steps of this algorithm, and every time so Q always gets updated just by squaring it. So there would be a multiplication gate that just squares Q. So this is how the gates computing the evolution of Q over the execution of the algorithm proceed. It's just repeated squaring. Whereas P, you would have some circuitry to do this. So you'd have the bits of EJ here, EJ1 up to EJ log m, and it just does this for each. So it's a little gross to write as a circuit, but you have some addition gate, and what feeds into that addition gate is like 1 minus EJK. Whatever K, let's say K is 1, so you get 1 minus EJK, and then you multiply that by P, and then you sort of do the same thing, but also you product Q in, and then add the two together. So yeah, it's not going to look I don't think it's going to be helpful for me to write that out in any more detail, but you get the idea. So in summary, this procedure, to take each term Tj minus R and raise it to the power Ej, is relatively, it's a little gross, but it's relatively straightforward, and the circuit isn't that big. You would, I kind of sketched it right here where it has log m layers and like a constant number of gates at each layer. And in that's it. That's ARIA. So just to summarize here, this is what the final circuit evaluation instance looks like. So the prover at the start of lookup argument has committed to A, right? And then the prover commits to these Well, let's say also someone honest in pre-processing has committed to T. So we can also include the table entries T as part of the input. So A has length M and T has length N. And then the prover commits to these multiplicities E1 to En. They're specified by bit vectors because each multiplicity is like a number between 0 and M, and there's this annoying off by one thing, where you need actually log of M plus 1 bits to represent a number between 0 and M. And after the prover's committed to all these three things, there's the verifier sort of picks this random field element R at random field element. Then the circuit, for each entry of A, it, subtracts R from it, multiplies out the results with a binary tree of multiplication gates, thereby computing the relevant information about A for the permutation check. Again, we're trying to check that the vector A and the vector obtained by T by repeating, each TJ, EJ times are permutations of each other. So this gate is computing the product of AI minus R as AI ranges over all entries of A. And then, here we have a subtraction gate for each entry of T, subtracting R from it. And then we want to raise each of these subtraction gates to the, the jth subtraction gate to the ejth power. And so you just have some circuitry that sort of, independently for each subtraction gate implements like the square and multiply algorithm, log M times, feeding into it, like E1 gets fed into, the square and multiply algorithm for, T1 minus R, E2 gets fed into the square and multiply algorithm for T2 minus R, and so forth. So each subtraction gate for an entry of T gets fed into some square and multiply algorithm. The results of the square and multiply algorithms then get, so let me just have one last square and multiply. And then the results get grand producted. So you have another binary tree of multiplication gates, to product out the results of all the square and multiply algorithms. That winds up computing. So this gate here computes the product from I equals 1 to N of T, I guess I was using J, TJ minus R to the EJ. And you just want to confirm that these two grand products spit out the same thing. So that's your circuit. The circuit has the number of gates in the circuit is like N log M. Basically, a constant fraction of the circuit is just specifying the multiplicities bit by bit. Then the square and multiply stuff actually has about the same size in terms of total number of gates, up to a constant factor as just the multiplicities themselves. So the total circuit has size order M log M. And so if you, apply like any snark to this circuit, you get out, the prover winds up just committing to order N log M field elements in total, kind of one per gate to the circuit. Another thing to point out here is this circuit has lots of repeated structure. So this whole nuisance that we've discussed kind of every time we talked about a snark, we always had to talk about like wiring polynomials, like add twiddle or malt twiddle. And in this circuit, add twiddle and malt twiddle can be evaluated, at any point in log like M plus N time. So that's not a concern here. You do not need like the prover or someone honest to commit to these polynomials in pre-processing to apply, Spartan or GKR based snark or what have you to the circuit. And that's it. And then, the comment before stands that if you, the whole input to the circuit has kind of already been committed. And so and the circuit has logarithmic depth. So you could apply the GKR protocol to this circuit, and the benefit of that would be the prover does not cryptographically commit to any values other than the inputs to the circuit, which were sort of already committed. The downside is bigger proofs, and there are sort of ways to get the best of both worlds, whether it's through limited use of commitments to gate values, sort of at the parts of the circuit that have fewer gate values, but make up most of the proof size in the GKR protocol. Or another thing you could do is try to use recursion. You do have to be careful that the GKR verifier doesn't do too many, hash evaluations after you apply fiat Shamir to make sure that, when you turn it into a circuit to then recurse upon, that circuit isn't too big or anything. So that's ARIA conceptually. So let me just pause here, see if there are any questions. I might have one more remark or something before we call it a day, but that's all of the technical content I wanted to cover today. So does anyone have a question? No questions?
I guess what's the relationship between lookup arguments and permutation checks, maybe?
Yeah, so lookup arguments tend to use permutation checks, like, as a core part of the permutation argument. A lot of people think lookup arguments and permutation checks, I guess, are like basically the same thing. I don't think that's the case. I think permutation checks are a key tool that one, that naturally arise when one tries to design a lookup argument, but I don't think they're the same. Is that enough of an answer?
Yes. And so when you do memory consistent check, can you replace the permutation check with lookup?
Okay, so memory consistency is basically, you could think of it as checking it as like a lookup argument, but not for a fixed table, but rather for a table that's dynamically getting written to over time, over the course of the reads. Reads are interspersed with writes. So lookups are like of the form. I want to make sure that each entry of this committed vector is in the table. But okay, let me go off on a tangent here real quickly. So there are two kinds of lookup arguments in my view. The ones I talked about today are called unindexed lookup arguments, unindexed lookups, and that's where like the prover is claiming, that each entry of A is somewhere in the table, but the verifier doesn't care where. Okay. Then there's something called index lookups. This is my personal terminology, where now the entries of A, is basically tuples. AI is a tuple, and it's basically some index J and some value. Maybe I'll just call it. I just need a name for a value. I don't know. VJ. I don't know. Yeah. J comma. Well, let me just say J comma V. Okay. So each entry of A is actually like a pair. It's like J comma V. Okay. And in index lookups, the prover is claiming that the jth entry of T equals V. So, unindexed lookups are basically like set membership. It's like batched set membership queries, making sure that each entry of A is somewhere in the table, where each entry of A is just a single field element. And index lookups are kind of doing a lookup into a particular entry of the table. Okay. And to finish this tangent, there's actually a straightforward reduction whereby you can turn index lookups into unindexed ones. That is, if you have any lookup argument like ARIA for unindexed lookups, you can use it to give one for index lookups. And the way you can do that is you can just what I call it pack J and V into a single field element. Okay. So what I mean is, let's say that the verifier knows for sure that both J and V are. How do I want to say this? Actually, I guess the way I've written this, let's just say that J is between 0 and N. I don't know. Let's say that. Then you could interpret JV or turn it into this. That's like a pair of field elements. One being like an index into the table, one being a value. You could turn it into the single field element like J plus N times V. And you think of this as the field element whose representation in base n is the tuple j comma v. Okay, so conceptually, like this tuple j comma v and this field element are like, they're like the same thing, but formally they're not. This is like a pair of field elements and this is a single field element. So you're just kind of packing the pair of field elements into a single field element. Now this does require that, that your field, or even like the characteristic of your field, be at least, whatever the maximum value of this is, which if your table is huge, that might be a problem. Furthermore, you might need to do a range check here since the j comma v was like committed by the prover. You don't trust the prover, so you can't know for sure. It depends on context whether you can be like promised without a range check that j is actually no bigger than n. If j is bigger than n, then you can kind of this packing might kind of munge together j and v in a way you don't want. Okay, so summarizing, if you want to do index lookups, what you can do is you can take each tuple in the committed vector A, and now the entries of A are tuples. You can pack them, each tuple, into a single field element, and now do an unindexed lookup into the table, which is also packed, whereby we replace, if you have a table where like tj equals v, you replace that table in the lookup argument with table t prime, whose jth entry is the packing of j and v. So what did I say? J plus n times v. And you do a lookup into this table. And the point is like the tuple, tj equals v if and only if like the packed field element corresponding to j comma v lives somewhere in t prime. Okay, so that was a lot to follow, and it was a tangent, but I think it's a pretty important distinction. So today we talked about unindexed lookups. In a lot of contexts, you care about index lookups, but fortunately, if you have a lookup argument for unindexed lookups, and ARIA is an example of one, you can also handle index lookups up to these caveats about your field maybe needing to be big, and you may be needing to do some kind of range check. But let's not get hung up on those details. Good. So now memory consistency checking. That's basically doing some kind of index lookups. So memory consistency is basically index lookups, but it's not into a fixed table. Not if the algorithms are allowed to repeatedly write to memory cells like standard computer algorithms are. So it's index lookups into like a dynamically changing table. And the table here, what I really mean is just like the computer program's memory. All right. So hopefully that is a little bit helpful to characterize memory consistency in that way. And it shouldn't be surprising, permutation checks, it's like a useful tool it's used in many lookup arguments, basically like in all of them. And similarly, permutation checking is a crucial tool used in memory consistency checking, where the prover, takes the time-ordered execution trace of the computer program and like resorts it to be grouped by, which memory cell was accessed. The regrouping makes memory consistency checking straightforward, but you still have to check that, the second execution trace that's committed is a permutation of the first, right? So I think permutation checking is just a tool that's arising in the lookup argument. It's also arising in this memory consistency checking, which is in some sense like a strictly harder problem, even though the solutions have comparable costs to lookup arguments, I guess. And it also arises like in something like Planck, which is not explicitly doing any kind of memory consistency checking or lookup argument. It's just a general purpose backend for circuit sat, but like in the guts of that backend, it turns out to be useful to check that two things are permutations of each other. So I just say permutation testing is it's a tool that naturally arises in lots of settings. But all of these settings are trying to establish some kind of consistency conditions. So, it's not a coincidence. Like, memory consistency is making sure that every read returns the last value written to that, cell. lookup arguments make sure that kind of, every read, like if the prover is sort of claiming that tj equals v, this is like a read into a fixed memory, and Planck, it uses permutation checks, I guess, specifically for making sure that, like, I think I forget, it sort of has the prover commit. Hope I don't get this wrong. I always need to get Planck back into cache, but commit to the value, not just of all gates in the circuit, but all wires in the circuit. And you need, that means you have to check that every wire leaving a single gate, is assigned the same value. And separately, you have to check that value, like, is actually the appropriate, like, sum or product of the two neighbors of that gate. So that value has to sort of be checked for correctness separately. So, like, equal to the appropriate sum or product of other values. And so that's also kind of consistency checking. That every wire coming out of a gate, you could think of the gate like as a memory cell. That memory cell is assigned a single value equal to the value of the gate in the circuit. And you could think of the wires as like reads into that cell. And in that sense, making sure that every wire leaving a gate in the circuit has the same value is exactly memory consistency. But in this case, it'd be like, I guess, some kind of people call it an immutable memory. This is actually what's used in Cairo. I think of it as like a write once memory. So basically, you don't know, like, in advance what the value of every gate in the circuit will be, but like as the prover like evaluates the circuit gate by gate, like for each gate, it winds up learning what the value is, and kind of you think of that like the prover as like writing that value to a memory cell, and it can't change that value once it's written to that cell. And then making sure that every wire leaving that gate is assigned that particular value that was written to the corresponding cell is just a memory consistency situation. So yeah, I don't want to overstate my case that like permutation checking and memory consistency and lookup arguments are not all the same. I think that they wind up looking very similar and with good reason, but I don't think they're all the same. Okay, I'll stop rambling there. Any other questions? I'll follow up to that one since it was such a rambling, strange answer.
Yeah, it makes a lot of sense. But I have some follow-up, but I will let you finish.
Okay, let's see if anyone else has a question. Anyone? Going once? Twice? Okay, go ahead with your next question.
Okay, so you can do memory consistent check with KZG-based index lookup, right? If I'm understanding that correctly.
Yeah. So when throughout even like today's lookup argument, right? I said the prover commits to A, prover commits to T, so an honest party committed to T in pre-processing. The prover commits to these multiplicities. In general, you can use any polynomial commitment scheme to commit to them. Which kind of polynomial you want depends on what kind of snark for like circuit sat you ultimately want to use here. And so if you want to use something sum check based, then you want to be interpreting these vectors as take their multilinear extensions and commit to the multilinear polynomial. But most snarks today, most lookup arguments used today, they're not using sum check, and they KZG commitments are particularly popular, and the Calc line of work, from Calc to CQ, they're all actually very specialized to KZG commitments. And so yeah, whenever you use KZG commitments, people tend to index these vectors by root to unity and stuff like that. So it's certainly an option. And if you're going to be using KZG commitments, that tends to be how people do things to ensure that, the standard reasons, make sure like certain quotient polynomial or vanishing polynomials are sparse and things like that.
Yeah. And this memory consistency check is it's like in the VM context, right? It doesn't.
Yeah, that's where memory consistency, as I've defined it anyway, comes up. It's when the prover's claiming to have run like a virtual machine or CPU or whatever you want to call it for a certain number of steps, and the virtual machine is allowed to like read and write to memory, and then memory consistency is required because the prover is claiming it ran this program correctly. But you don't trust the prover. So there's sort of two aspects of correct program execution. Like one is you can kind of cut what the computer does in half. You kind of have memory, and memory consistency just basically means the memory is operating correctly. So every read returns the value last written to that location, and the other half is like everything else. So basically, every time a primitive instruction is executed, it spits out the appropriate output given the inputs. And yeah, so that's what memory consistency refers to, is like the memory part of running a computer program. Does that make sense?
Yeah. Yeah. Do you have anything else you want to cover in this session? I will let you finish if you.
Oh, no, this was it for today. I guess I maybe was going to just make one more remark, which is like, the way I presented ARIA is not the way you normally see lookup arguments. So what I presented ARIA completely as like a front end technique. Okay, so what I've done is I've described a circuit that basically has a satisfying assignment if and only if like the prover's claim in the lookup argument is true, more or less. So I've described ARIA as a front end technique. Okay. Most people think of lookup arguments as back-end techniques, and I think that's somewhat reasonable, even maybe the right way to look at them, because I actually defined a lookup argument to be a snark for a specific claim, namely that the prover knows an opening of this commitment to A, such that each entry of A is somewhere in the table. And snarks for specific statements are exactly what backends are. Like a snark for circuit set is a backend, and that's a snark for the statement, like I know a satisfying assignment to this circuit. I think the right way to view lookup arguments is kind of as straddling front ends and back ends, especially because once you have the power of a lookup argument at your disposal, the way you design front ends might change quite a bit, because you can kind of put a lot of like kind of the work that a circuit might otherwise have to do into lookups. And, the circuit itself that the front end spits out kind of only winds up having to implement, as addition multiplication gates, stuff that the lookups somehow are not handling on their own. But I think that this perspective of a lookup argument as purely a front end does clarify some confusion out there, because there have been repeated claims that like snarks for R1CS, snarks targeted at R1CS, like cannot interface with lookup arguments. And that's just like totally wrong, right? And this perspective that I used today, I think should make it clear that it's wrong, because here I described the lookup argument just as like a front end that spits out a circuit. And a circuit is a special case of R1CS. So if you have a snark for R1CS, you also have a lookup argument, and you can just combine the two kind of trivially, even if you went through, like one way you could do it is just have the R1CS like implement this circuit here. And there you're like part of your circuit will be everything that's not happening in the lookups. And the other part of your R1CS instance will be just implementing this circuit here, which is ultimately performing a lookup argument effectively inside of it. So just a little hand wavy, a high level rambling about how lookup arguments sort of straddle front ends and back ends, and actually typically can be described, if you want, as a front end. And I don't think one should literally like write down this circuit as a circuit and apply like a snark for circuit stat to it. You should sort of munge the front end and back end together, like kind of look, this is one very specific circuit. You should just sort of more directly give like a snark for this particular circuit. But conceptually, I think it's helpful to describe an actual circuit here. Let's see, is that the last thing I wanted to say? Okay, I guess the final, very, very final comment. I just lost my So the nuisance here is that in order to make the square and multiply algorithm efficiently implementable, like in a circuit, we had to express the multiplicities as bits, as binary as bit vectors of length log m. Okay, you can kind of think of what Plukup's doing as avoiding that grossness. So specifying each multiplicity like as a single field element, right? So if E1 here like is the binary representation of the number 10, like in Plukup, you'll try to replace the log m bits in E1 with just the field element 10. That in some sense comes at a cost in something like Plukup, because the costs turn into like 5 times max m and n, and so like which depending on, so basically there's more costs in Plukup that depend on m than in aria, but it avoids this law, it avoids the n log m term. It gets rid of that log m. So I'll say a little bit more about Plukup next time, although I won't cover all the details. So I wanted to highlight this log m factor is coming in because of the nuisance of implementing square and multiply inside a circuit, which kind of needs access to the binary representation of the exponents. And there are ways you can try to avoid that log m factor. And they do come at some kind of price, and you wind up, one is better in some parameter regime, m versus n, and the other is better in the other. Okay, so that's everything I had to say today. So please, more questions.
Okay, so one thing I've heard people discussing is like for front ends, there's the circuit approach and the VM approach, and I think they've talked about some trade-offs, but like, do you have any comments on that?
Yeah, I think I tried to talk about this a little bit last week, but of course, last week was 2 hours of rambling discussion. But I think the high level, I try to explain this with the matrix multiplication example. So, if you have this computer program that takes as input 2 n by n matrices and goes to multiply them with naive matrix multiplication, with 3 nested for loops. So the output, plus equals AIK times AKJ, BKJ, right? Like, this like directly corresponds to a circuit directly, that just, does each multiplication operation and each addition operation. And, I guess, I sketched a little 2x2 example last week, I think, but I won't spend time doing that again. And so it is possible to take like a special computer program like this and sort of turn it into a circuit with like no overhead. The circuit, like, circuits kind of are like straight line computer programs that only do addition multiplication over a finite field. Okay, if you applied like a ZKVM to this program, you would get a much bigger circuit. Okay, because the circuits that the ZKVM spit out, they sort of run the CPU for some number of steps, and each step they have to include, like some logic or something, some gates, some constraints for the CPU to figure out like which instruction should be executed at this step, and then execute the instruction. So there'd be all this extra logic to figure out, well, at this step, it's my time to multiply these two values. And, let me also like read this particular entry of A and this particular entry of B. And let me read this, write it to this particular output value or something. At this step, let me figure out that it's time for me to do the addition, not multiplication, whatever. At this step, it's time for me to like advance the counter K from 15 to 16 or, what have you. And that's just like extra stuff that the circuit is doing that doesn't intrinsically need to be done if you didn't insist on the circuit implementing like this virtual machine abstraction. So I think, that's kind of the cons of the virtual machine abstraction. The pros are, I guess there are a bunch of them, like the circuits that come out of these ZKVMs are like inherently, uniform because they kind of just apply the transition function of the virtual machine over and over and over again, which means, you never have to deal with an honest party in pre-processing committing to like these wire polynomials add and mod, or in Marlin it'd be like, these bivariate extension polynomials of the R1CS constraint matrices and stuff. So that's a nice benefit. So the circuits might be bigger, but they're nice and structured and regular. Also, you can you can have like a universal circuit in the ZKVM approach. Basically, like one circuit that works for like all computer programs up to a given length. And because these front ends, like actually running them can be like pretty expensive. Like turning the computer program into a circuit, that can be pretty bad. People don't really think about it because they're like, oh, I only have to run this like once per circuit. But especially if you're like changing your circuit a bunch or whatever, like it can be pretty gross to like actually run the front end. So to have to generate like the circuit, like run the front end only once, like forever, is pretty nice, up to a certain time bound. Yeah, let me think. Maybe I should stop there, but that gives you some sense of what my view of the various trade-offs. So I think in general, there will always be considerable overheads to the ZKVM approach. In certain, specific applications, maybe we won't necessarily know a way to a better way forward anyway. But in many others, if you actually didn't insist on the circuit sort of literally running the CPU for some number of steps, you could make the circuit significantly smaller. And yeah, people generally like the ZKVM approach, like seems to be leading to like more usable tooling. I don't think it inherently like tooling that goes through the ZKVM approach has to, fundamentally be more usable. But that seems to be the way things are just going today. So, like the aspirational idea is somebody will write a program in whatever language they want, whether it's Rust or Python or something, and that will get compiled down to like RISC-V or what have you. Then you apply like a ZKVM for the RISC-V CPU. And you don't hear about efforts so much to do the same thing, but without going through a ZKVM, whether it's the RISC-V instruction set or Cairo or the EVM or what have you. I don't think there's anything fundamental about that. I think there's no inherent reason you couldn't take a high-level computer program in Rust or Python and apply a front end to it that doesn't spit out a circuit like that, runs a primitive CPU for some number of steps. But I don't hear about people designing tooling in that vein today. Okay, I'll stop rambling. Was that a helpful discussion at all?
Yeah. Yeah. And any comments on Nova-based VM?
Yeah, I think it's. I'm optimistic about it. I think there are some technical challenges that are not difficult to overcome, but will need to be dealt with. like the memory consistency checking stuff we discussed is a little trickier to do with something like Nova as the backend, because you can't actually, with IVC schemes, with folding schemes, this technique of the prover, like, committing to an entire execution trace just doesn't work. Okay. If you just think about it, like the whole IVC schemes, the whole point is like the prover's committing to some small vector like many, many, many times, rather than committing to one big vector all at once. So it gets a little trickier to do memory consistency if you want your backend to be like something like Nova. But I know there are ways to deal with it. It's probably worth putting in a paper at some point, since I think many people are not aware of the best ways to deal with that. But other than that, yeah, I think I stated sometime in a relatively recent session. I think I discussed this a little bit, which something like Nova is tailored to what I call iterative computation, which means you apply a simple step function f many, many, many times to some start state. And I said, again, I don't know if it was in this session or not, I said that this seems very restrictive to take the same simple function and do it over and over again, but this is actually capturing general ZKVM, general CPU execution, where f is just the transition function of the CPU. It's like one step of the CPU. And the only thing missing here, when I say that, is memory consistency. So, and that I have already discussed, how it's like you can't use the same technique that we discussed last week, because that involves the prover committing to the entire execution trace of the CPU all at once. But there are other ways to deal with it that should be okay. So yeah, I guess just one more comment is I have this new lookup argument that coming out soon, and like the first thing we're applying it to more as a demonstration of the power of the lookup argument than any kind of stamp of endorsement of the general ZKVM paradigm. But we're going to give like a new and more efficient kind of ZKV, like SNARK for virtual machine execution. And initially, the backend used in the our ZKVM is just going to be Spartan, but I would like it to be Nova. And there are some additional questions about how to fully integrate our new lookup argument with Nova, because our new lookup argument, it's exactly what it has a similar issue. Like you saw today, like the prover committed to these multiplicities today all at once, right? So that's a little bit difficult you can't just do that with Nova for the same reason I said before, like that the prover can't commit to an entire execution trace all at once if Nova is your backend. So you need to do some extra stuff to address that. And it's closely related to how one would deal with memory consistency if your backend was Nova. So short version, in summary, I guess, I do think Nova is extremely well suited to ZKVM, as a backend for ZKVMs, because CPU execution is exactly the sort of iterative computation that Nova captures. There are, however, some just nuisance details because CPU execution involves memory consistency, and similar issues come up if you want to use a lookup argument. And there's probably no coincidence that if you look at Hyperplonk, Hypernova, it involves a new lookup argument called the lookup, where the N is for Nova, and that was sort of meant to address exactly what I just said, address the issue that the prover can't commit, with Nova, can't commit to a giant witness all at once. So I think hopefully within the next year or something, there'll be major progress here. And again, one really nice thing about using Nova as a backend for ZKVMs, as in basically all applications of Nova, is space efficiency of the prover. So if, today, like even applied to very small circuits, a lot of snarks, the ones that use Fry in particular, will have like hundreds of gigabytes of prover space. With Nova, if you're careful about how you implement, how you turn F into a circuit, some of these libraries just use massive amounts of space just completely unnecessarily. So if you're a little bit careful about it, the prover should be able to just run the virtual machine. That virtual machine needs some amount of memory, like just to run it, and then to compute the running like Nova proof of the correct execution of the virtual machine, up to date, up to now, however long the prover's run it for in its head. Really, the prover should only probably need like 30 megabytes of space or something. And so that's just sort of a night and day difference compared to what a lot of people are doing with ZKVMs today. So if you want the ZKVM prover to run in the browser or on a phone or something like that, I really think there's literally probably not any other option long term but to do something like Nova.
And you get time efficiency as well.
Yeah. So basically, conceptually, in Nova, like all the prover does is like take a circuit computing, the step function of the CPU, and commit to the value of every gate in the circuit, and it just does that over and over again, one per step of the CPU. Now, so that is no more expensive than what basically any snark people use today do, right? Because the very first thing that the snarks people use today do is commit to a value for every gate in the circuit. It's the same cost. So there's no like sort of extra work in Nova for the prover. In fact, there's typically kind of less work for Nova for the prover, because that's really all the prover does. Whereas in other snarks, the prover does other stuff as well. Now, there are some additional technical caveats that I think research needs to continue to address, which I guess I forgot to mention this in my rambling before about Nova as a backend for ZKVMs. So that's like things like the supernova, issue, the issue that Supernova was trying to address, which is, okay, so.
Non-uniform.
I think that I don't like that terminology. So I'm going to put my own little spin on how I would frame it. Something like primitive virtual machines. The EVM has 140 instructions or something. The RISC-V has 60 instructions or something. Cairo has, I don't know, 9 primitive instructions or something, right? And with standard snarks, like not Nova, with what I call monolithic snarks, where you sort of take a circuit and just apply the snark prover to the circuit, and like that's it. Or maybe you take a big circuit and chop it up into some pieces and prove each piece and then aggregate the proofs, but it's still not full-fledged like IVC. In those settings, we know how to avoid this making the circuit kind of execute every possible instruction at every possible step of the computer program. Okay. So a priori, if RISC-V has 100 instructions or something, you don't know in advance for each step of the computer program which of the 100 instructions will get executed. So if you're very naive about how you go about things, you would wind up with a circuit that actually just like kind of literally executes all 100 instructions every step, and then just sort of ignores everything other than the one instruction that actually got executed in that step. Okay, so we have ways to avoid that horrible overhead, which asymptotically doesn't really show up in the asymptotic bounds because we think of 100 as a constant, but it's a big constant. But concretely matters a great deal. Okay, with Nova, because it's iterative computation model is a little bit more restrictive than what happens in these monolithic snarks. We don't know how to avoid that. So Nova would kind of have to the circuit implementing F would actually in Nova have to kind of have logic to implement every possible instruction of the ZKVM at every step, which is really untenable. this doesn't come up with something like a VDF, which is so simple that there's kind of just like one instruction getting executed over and over again. But with like ZKVMs, there'd be like 100 of those instructions, and it'd be no good. So Supernova addresses that, but it kind of forces the prover to run, like if there are 100 instructions, it kind of forces the prover to run like 100 different instances of Nova at once. And it's just like at each step of the computation, it only sort of needs to update or needs to pay attention to the one instance corresponding to the one instruction that actually got ran at that point. And so, there's it's maybe not as ideal as you could like, because this 30 megabytes of space might turn into 30 times 100 megabytes of space, stuff like that. So I think there are open research directions that still need to be addressed to really get like an ideal Nova-based ZKVM. But I think, Nova's still pretty new. The community is still sort of absorbing it. I think they're pretty far along now, but, it's just, we haven't really spent that long trying to address these issues. So I'm optimistic that kind of all of them will get addressed in due course, and Nova will be like some future analog of it will be some really, really good backend for the ZKVM approach. Hopefully all this discussion is helpful and not just rambling and incomprehensible.
Yeah, it's very helpful. I guess one last question is there like a ZK friendly instruction set? Cause in like traditional snarks, it's like the addition and multiplication relationships are easy to prove, and now we have like range proofs. It's like, so these three operations are snark friendly, kind of.
Yeah, so I mean, I'm going to give you my personal view on this. First I'm going to tell you what my impression is of the sort of prevailing view, and then I'm going to give you my view, which is different. Okay, so I think the prevailing view is like basically, that the snark-friendly instructions are like straight up like addition, multiplication over a finite field. Maybe anything that's sort of capturable directly by like very low degree constraints, if you will. Maybe like reads into some kind of limited memory. And I think that the prime example that takes this to the biggest extreme is Cairo, right? Because the number of primitive instructions there is like under 10, two of them are just like addition, multiplication over a field. The memory is this immutable thing I mentioned before, where you can write to a memory cell once, and once you do, you can't overwrite it. And in fact, also you need like to write to like a contiguous sequence of memory values. So you can't have like kind of uninitialized cells like in between ones that are actually like read. And there's the reason one would design a VM that way is exactly because of the belief that one should restrict, it makes sense to restrict to like the snark friendliest possible instructions for performance reasons. But of course, this comes at a price, because the stuff people actually want to do is like not addition, multiplication over a field and reads into limited memories, right? They want to read into like, just a standard read-write memory, and they want to do like addition, multiplication like your laptop does, and they want to do like bitwise operations and so on and so forth. And so, you would have to combine you need a compiler that would take like a higher level. You do one of two things. You either make the developer directly code in like your assembly language for your very primitive CPU, which is like placing a heavy burden on the developer, or you let the developer code in like a higher level language, but then you need a compiler that's going to turn the high level program into like a program for your very, very primitive, like very snark friendly CPU. And that is basically my understanding of what like Cairo 1.0 is they've had a much more developer friendly higher level language, like inspired by Rust. It still has like a few strange limitations. There's still the immutable memory. There's like unsigned integers, but there's no, there's no signed integer data type. So, just some like kind of strange still restrictions, but much better developer experience. But, there's just the question of like how much overhead is it to, if you let the programmer write the program they want, that's easy to express. You still have to turn that program into instructions in the very, very limited instruction set. And so, that's going to just have a lot of overhead. Like, one line in the high level program might turn into many lines in the very restricted, primitive instruction set. Okay, so this new work I have coming out, I think, I'll just like shill it and hype it here. Why not? My interpretation of it is the following. It's suggesting that like surprisingly complicated instructions, such as, for example, all of RISC-V, which is certainly like a more expressive and less snark friendly in most people's minds instruction set than Cairo, are just as easy. I'm going to call them like just as snark friendly as the ones people think are snark friendly today. So that there's effectively no performance difference between restricting your primitive instructions to say whatever Cairo uses versus going to more expressive instruction sets like RISC-V or maybe even beyond that. So I basically think it's a we'll see details soon once I'm ready to like talk about it. But things that look like they should not be easy to implement over like a finite field of like large prime characteristic or something. In fact, through like the magic of the sum check protocol and lookup arguments, actually can be implemented. In snarks, basically, it's just getting done inside the lookup argument at no additional cost compared to like a single field multiplication or something. So I shouldn't say it's way too strong to say no additional cost, but like so roughly speaking, I think we might have a snark for like every RISC-V instruction, where the cost of executing an arbitrary RISC-V instruction for the prover is actually like less expensive than like applying like the cost of a single addition or multiplication gate in Planck, right? So if I tell you like, I have a snark for RISC-V where the prover time spent proving each RISC-V instruction is less than a single additional multiplication gate in Planck, that sounds maybe kind of crazy because it's almost like saying the RISC-V instructions are no more complicated than a single multiplication gate or a single addition gate. And there's something like that is basically true. So I think perspectives on what is a snark-friendly instruction set might start to shift soon. Hopefully that makes some sense and wasn't too self-indulgent.
Very interesting. I'm looking forward to this. This remind me, like, I think historically, there's a lot of people using like Boolean gates, and somehow it shifted to arithmetic gates.
And there's a lot of papers on this now too. So I think people have this sense, which I also think is inaccurate, that there was a time when people thought we might work over fields of characteristic 2, going back to, I don't know, let's say 2018 and before. If you look at early papers on Fry, they talked about using like additive subgroups, and it's because those are pretty nice to use when you use a field of characteristic 2. But now it's all multiplicative subgroups, and everyone's working over fields of like large prime characteristic. I consider even like 2 to the 32 or 2 to the 64 to be large in this context because it's not characteristic 2. Okay, and Yeah, of course, anyone who wants to use elliptic curve based techniques definitely wants to work over a field of large prime order, because those are the fields that, play nicest with elliptic curves and stuff. And as a result, people think that like bitwise operations are gross to do, especially if your field is really big, because they roughly think that the best way to do those operations is, you take a field, let's say you take two field elements, A and B. They're both field elements, and you want to sort of look at their binary representations. Let's say A is, represented by 0, 1, 0. I don't know. Here's just some bit string. And you want to do some bitwise operation on the bits. You want to take their bitwise or something like that. And I think people still have in their head like the old way of doing this stuff, sort of pre-lookup argument, where the way, if you're working over a field of large prime characteristic, taking bitwise or of things doesn't look anything like field addition or multiplication. So what people have in their head is the prover commits to these binary decompositions as like advice inputs. And once you're given the binary decompositions, it's like easy to take bitwise or something, and then like pack the results back into a single field element. And this seems very wasteful, right? Because you're assigning like a full field element to each individual bit. It's like if you have a 256-bit field, it feels like you're just wasting 255 bits, right? This new lookup argument I have coming out, like I think should hopefully drives home like you don't have to do this. And I think even with today's lookup arguments, you don't have to do this. Like okay, so if you're dealing with like 64-bit data types here, so each of A and B is 64 bits. Okay, like you can't have the new work I'm describing is conceptually going to involve a lookup table that's literally just like the whole evaluation table of the bitwise operation. So it would you'd have a table that has indexes its input by two 64-bit vectors xy, and the xy table entry is just like the bitwise or of x and y. And so this is the table of size 2 to the 128, which is of course way too big for any lookup argument today. And the new lookup argument is conceptually it's going to kind of handle such a big table anyway, and just not make the prover materialize the whole table, kind of only materialize elements of the table that actually arise in the computation. But under the hood, it's doing something that actually lookup arguments could do even today, which is just use something I call decomposability of these primitive instructions, which is if I want to know the bitwise OR of x and y, like what I can do is I can break x and y up. They're 64 bits each. I can break them each up into say like eight pieces of 8 bits each. So I can break them into 8 pieces. I don't know if I'm drawing 7 lines or not, but so like 8-bit pieces. I can bitwise OR each piece individually. Okay, and that can just be a lookup into a single table size 2 to the 16, an index lookup, right? So I do 8 lookups into into a table size 2 to the 16, and then I get the bitwise OR of each piece, and then I can like just glue the pieces back together into a single field element, just like pack them all together into one field element to get the result of the bitwise OR on the 64-bit pieces. So you can do this today. And like eight lookups into a table of size 2 to the 16 might be much better than taking like 128-bit decomposition, depending on like what lookup argument you use, and how many lookups you're doing, and how many bitwise ORs you do over the course of the computer program or something. So yeah, there's just this view that since people work over fields of large characteristic today, that bitwise things are like extremely unfriendly to snarks. I just don't think it's the case. And like even with today's lookup arguments that need small tables, I don't think it's the case. And with this new lookup argument coming out that does something very similar to what I just sketched here, turns a lookup into a giant table into a bunch of lookups into smaller tables. I think that'll even push the message further. These bitwise things just can be done over big fields. It's not so bad. Yeah.
Yeah. I actually mean like historic, like 10, 20 years ago, I think. Like, cause the last the latest paper I read about Boolean gates is I think it's called ZK bool or something.
Yeah. So, I mean, that people are doing this work now where, they're designing snarks for Boolean circuits. There's been some nice ideas there. There's work that's trying to get the prover to be, linear in the number of gates in the circuit. But here linear means like a linear number of field operations. If there are S gates in the circuit, you want order S many field operations where the field itself is like not much smaller than size 2 to the lambda, where lambda is a security parameter. So that we already know how to get linear time if you allow yourself to work over a field of size 2 lambda, but they consider this to be like kind of a too big a field, and that's a very reasonable view. My I guess skepticism a little bit. I don't know if skepticism is the right word, but my view is looking at Boolean circuits. Is sort of insisting, it's baking into the problem that the prover has like decomposed field elements into their bit decompositions. I say, so the goals here in these works are to try to work over a small field, bit presumably because they don't like the idea of like a bit decomposing a large field element into its bit decomposition, and like assigning a single large field element to each bit in the Boolean decomposition. Okay. I think that might be missing, that you can do things like I sketched above, where you can implement bitwise operations over a large field in a snark without doing something like doing a bit decomposition of a large field element into its binary representation, and like assigning a full field element to each of those bits. So my take, like, I am not looking at like better snarks for Boolean circuits, right? I think the right approach is to just never go through Boolean circuits, just work over a large field at all times. And if you want to do, bit operations over the bit representation of a field element, like we have ways to do that that are better than doing a full-fledged bit decomposition. So just kind of rambling personal views. I think there might be good ideas that come out of looking at Boolean circuits, but I'm not sure it's one should ever be going through Boolean circuits in the first place, sort of.
Yeah, makes sense. I think I don't have any other questions. Thank you very much.
Yeah, always appreciate the questions. I hope the discussion is useful. Okay, let's wrap it up since it's been a long session. Thanks everyone who's still here for staying for so long. So next time we'll say a little bit about lookup, and then I'll start talking about sparse polynomial commitments, and maybe even start covering this new lookup argument if I feel like it's close enough to becoming public. So have a great weekend, and I'll see you next week.